So, welcome everybody, welcome back to Tonight's Micro's machine learning experience when we are going to do some convolution again. So, what is today's agenda? Is that, so last time we covered what is the convolution and how it works. So we used this very popular, well, what is it called, like a spreadsheet software to implement our convolution. So basically convolution is a matrix operation on one matrix using another matrix, or in this case it's like a tensors. So we already went through that. What is very important is when we are doing this kind of calculations, you have to remember that like this element will be multiplied by this element will be multiplied by this element. So in convolution, you are multiplying with the opposite item of the kernel and not like the one at the same position. There would be something else called correlation. So let's not waste our time and let's go to Python. So here I'll just use this the control enter function in the spider. So this is called spider. It comes with the anaconda distribution, so I can hit control enter and we'll execute all the lines between. There's a hash %%. So this is how this makes cells. Anyways, it doesn't matter. I got my weight matrix, my input matrix, and my bias factor from this file. So I pickled this and then I got them out of the pickle and now I have them here. So I can just, in NumPy, we're in NumPy, and unfortunately the variable explorer tells me this: arrays with more than 3 dimensions are not supported. So we have 4 dimensions. We can check the weight matrix. It looks like this. So this is 1, 2, and 1, and 2. So this is the 4 dimensions. X dimensions like this, Y dimensions the vertical here, the next dimension is here, and the next dimension is here. Well, if you are going from right to left. So when we are addressing, well, let's check the W, oh no, the X. So this, you can take a look at it better. So when you're addressing here the dimensions, this one is the last one. So this one is the next one is the vertical here. It's 2 because this is 1, this is 2, and this one, look at this 1, 2. Well, especially in Python, it's 0 and 1, but I guess you know Python. So here, if you don't, learn it. It's not that difficult. So basically we number our arrays from 0. So the x coordinate here is, well, actually I'm saying x, but this is actually, yeah, I'm making you confused, very confused right now, I know. So in the x tensor, so let's go through it again. Let me try to unconfuse this. So first is the number of the elements, the number of different data, like different pictures, for example, or different, I don't know, whatever. This is the one and this is the other one. So these are 2 different samples. Let's say these are 2 samples, and in all these samples we have 2 layers. So this is 1 layer in the sample, this is the other layer in the sample, and all layers have 4 rows, and all rows have 4 columns. So this is how it works in NumPy. So this is column 0, column 1, column 2, column 3. This is how you have to address them. And when we are doing the convolution, so let me start typing here. So we are going to go through the samples in a range of 2 because we have 2 samples. And so before we do that, we should make our y tensor. So this will be this tensor. So this will be our the product of this convolution operation. So this will be from NumPy zeros, and then the shape of this will be 2, 2, 3, 3. So we can, so actually the number of the samples will be the same as it will be in our x, of course, because every sample will be convolved, and this will have a convolved product, a convolved y. And well, the y will have layers so the number of layers will be determined by our weights, by the kernel. So this kernel has 2 for a layer number and 2 for depth. So this transforms a 2-layer tensor into a other 2-layer tensor. So that's why our y will have also 2 layers. And the x and y dimensions can be calculated based on both the stride and the padding. So we talked about the padding and the stride. So basically, this will be like if the x dimension of the input tensor is 4, so we have to add how much do we pad to the dimension, because the padded dimension there will be x plus 2 times padding, and then we have to subtract the kernel size and then divide by the stride and then add 1. So it's kind of easy to look up this formula, but you can also derive it for yourself. It's not that difficult. So that's how it becomes 3, because we are not padding x, we are doing stride of 1. X is 4. Our kernel is 2 by 2, so it's 2. 4 minus 2 is 2, divided by 1 because we are doing stride of 1, and then plus 1. The plus 1 is always plus 1 in the end. So let's go through all of our samples, and in all of our samples we are going through all depth in range 2 because we have a range of 2. So this is going to be the depth of y. So just to be clear here, I should add that. And so this is now we basically have to produce all these matrices. First of all, when we are going for this matrix, this will basically, we can try, say, so this is 1 to 3, and let's go first through, so each element of this y matrix, how should it be created? So for yx in range 3 and for yy in range 3, let's make it more consistent. So here we will have basically the y sample, y depth, yx, yy element. What should it be? Well, this will be, so let's just add a comment here saying we selected an element in y. And now we are going to do something. So we have to go through the layers of the depth of our x, which will be x depth in range 2, because and then we have to go through the following. So now we are going to go through wx in range 1. No, let's just do like range 2 like this, and then we are going through wy in range 2. So now we have selected one element in the convolution kernel. So basically what we have here is, let's see, so in the y x that no y, it's going to be sample y depth y x y. We will add to this the following. And this is when it gets tricky, so it's gonna be the weight matrix. And the weight matrix starts, if I'm not mistaken, yeah, the first coordinate is the y. Oh, not this one. I want to go here. Y depth x depth, and yeah, we have to go in the reverse direction, so don't forget it's going to be 2 minus wx and 2 minus wy, and I'm gonna try to make it one screen, and then we multiply this one. I have to decrease the text size for that, for you to see. Oh no, I can go back to this text size and just do like this. Ha! We don't need the console now. I'd rather you see this well. So now we are going to multiply this with the appropriate x value, which is going to be x sample, then x depth, and this is the tricky part. So here we have yx plus wx and y plus wy, and this should be it. So we have this y element, and so here we have the y element. So all these 3 iterations, these have nothing to do with which y element we are dealing with, but these 3 selects one item from the w, so the kernel tensor, and then it also adds so it multiplies the element from the kernel with the x. So you know this is the same sample that we are taking the sample for the y, and the x depth, well, we are going through the x depth here, and then we add, so this is going from 0, so this is also going from 0, so that's why we can add these. And here, because the kernel is going in the backwards direction, so that's why it's 2 minus wx and 2 minus wy. And of course, what we are missing here right now is the bias. So y And this is what I should have done here, because why not? So y sample y depth yx y equals bias y depth. So the bias is just a vector for each depth in the product of the convolution. We'll have one element. So let's see if it runs. Oh, what have I done wrong? Seems like maybe my Python knowledge is not sufficient here. Anyways, let's just get everything in one line. So you've seen what I've written there. Now I can just... Oh, the problem was not with my syntax. Index 2 is out of bounds for axis 2 in exercise, yeah. The problem was not with my Python syntax knowledge. Seems like, at least. So here we have the problem of having to use, because if it's numbered from 0, and this also goes from 0 to, so it's range 2 is like 0 first and then 1. So here, if I go in a sample in range 2, that means that it's going to be 0 and 1. It's going to be 0 and 1. It's going to be 0, 1, 2, 0, 1, 2. So it's going to be 0, 1, 0, 1. And if subtract 0 from 2, that's going to be 2. So that's not good. Let's do it again. So now it ran. There is no error message. We have all the variables here. So let's see what we got for y. Let's compare. Oh, damn. Oh! Yeah. Okay, so it's 0, 2, 1, 6, minus 1, 7. Not this one. 0, 2, 1, 6, minus 1, 7, minus 2, 3, 0. Looks okay to me. Yeah, so you can see that there is one problem here. What is not the same? This 9 is here, it's 5. So that 4 is there, 6. Minus 5, 6. 9, 7, 11. Minus 3, 6, minus 6. Is there any difference in the x tensor there? That can be the problem here. I think I did do a poor job of copying something from here to there, maybe. 1, 0, 1, 0, 0, 3, 4, 1. No, that's... Oh yeah, here is the problem. So here we have 3, 0, minus 1, 0, and 0, 2, 4, 1. And this is not the same. As you can see, this is a minus 1 here. So let's just correct this. And now my y tensor should be what I got here, not here, but here. So minus 5, 6. Yeah, 9, 7, 11. Yeah. Okay, this seems to be working well. Okay, so this is basically the most basic naive implementation of a convolution. And you can see here we have 1, 2, 3, 4, 5, 6, 7 iterations. And well, the problem with this is that as I watched a video about programming languages on the internet, and they said if you want a programming language that's slower than Java, then you have Python. So Python is slow, and when you are doing convolution, you are probably working on, most often you're working on images, which are huge matrices, and probably you are working with some convolutional neural networks, so you want to convolve a lot of samples together. And this case, this implementation will be too slow for you. So what I read on the internet is that you can basically linearize your samples, and this is how I implemented it in this kernel. So this is the image to columns. I have two ways to do it. It's the loops version. It has 2 loops, and well, it works. But there is one that's even more interesting, how it works. I read it on Stack Overflow, and I derived this myself too on the airport when my plane was cancelled and I was sitting at the airport for 4 hours. I had time to understand this. There is one implementation that's even faster than this, but that one was just too high level for my current Python knowledge. So how can we speed this convolution up? So what I was preparing to do for you is matrix operations. So how in a convolution, what do? We get the linear combination of a lot of numbers. So linear combinations, basically, you are multiplying numbers 2 by 2, 2 by 2, and then adding them all up together. So what does it have to do with matrix operations? So if anyone ever heard of matrix operations, so let's make a matrix here. Let's make another matrix here. Let's make it like this. And when I was in university and we learned about linear algebra and we learned about matrix operations, so matrix, you can add matrices together that are the same size. So you get like this matrix and another matrix, and then it's basically you add this element to this element, and then just don't format it for me, please, and don't just like this. Let's just write with random numbers. It's going to be random 6s. So this is how matrix addition works. But we are not interested in that because that's boring. Matrix addition is boring. Matrix multiplication, on the other hand, is much more interesting. Because in matrix multiplication, let's just make this random. It's very random matrix, if I can. So because matrix multiplication is not that simple. So you don't just okay, this is my random matrix. Yeah, because why don't prepare beforehand when you're making a YouTube video? Anyways, so matrix multiplication, you got linear combinations. And what kind of linear combinations, you might ask? Just leave it like this and make it like this. Very good. So You might ask, in a matrix multiplication, we multiply. So the matrices should have the following attributes. So this matrix is basically 1, 2, 3, 4, 5, 6 by 6 by 4. So when I want to multiply it with another matrix, that other matrix has to be 4 by something. And then the matrix I get will be 6 by something. So, what do you know about vector multiplication? So vectors, like if you have one vector, this is one vector, you have another vector. How can you multiply two vectors? Oh, what have I done? So how can you multiply two vectors? When you are doing a scalar multiplication. So in scalar multiplication, you multiply this element with this, add this, multiplied by this, add this, multiplied by this, add this, multiplied by this. So you have all linear combination. So what you've got there here when you're making the scalar multiplication of the vectors, it's basically very similar to in convolution, except adding the bias is just, we can consider like the last step, very last step. But before adding the bias, what you are doing is getting numbers multiplied together and then adding together. So when you know that there is this kind of vector multiplication, the scalar product of a vector, you might think about, why don't I just make my matrices and my kernels into this kind of nice, neat vectors, and get the final, the convolution, the product of the convolution, just the convolved final matrix, just as all the elements will be just this kind of vector scalars, scalar multiplication kind of things. So my good news for you is that it's possible, because matrix multiplication is basically like every element of this product matrix can be defined as, so what we were talking about, and I deleted it from here, such an idiot. So we have what, 6 by 4 matrix, and then we have 4 by 1, 2, 3, 4, 5, 6, 7, 8, 9 matrix. And our product matrix is going to be 6 by 9. And in a 6 by 9 matrix, we will have the following. So if we say this is I and j, the I and j elements will be the scalar product of the ith row of the first matrix, and the jth column of this matrix will be kind of the scalar multiplication, the scalar product of a vector. And you can see this description everywhere on the internet. And how I was taught to do this in university, because when I was in university, I had to do matrix multiplication on paper by hand without calculator. So how they taught us to do it is just get your sheet of paper, write down one matrix like this, other matrix like this, and this element will be the scalar product of this row with this column. This element will be the scalar product from here and here. So you can just write, multiply this element with this, then add, multiply this with this, add this with this, add this, multiply with this. So when we done the multiplication, I have to fix B here and 2 here, C here, 3, D with G, and E with 5. I hope. Come here. Oh, damn. Go back and again, try again. So no formatting, thank you. Yeah, it works. So this is how you can get the matrix product of two matrices. And then again, yeah, these numbers are too big, so let me, yeah, because everything is positive number, then this is what happens. So of course, what you get here is a matrix product. So how do you deal with this when you want to make a convolution? So my first idea was because before I started learning about the convolution, I learned a lot about basically regular neural networks. And regular neural networks, you can vectorize your solutions into this kind of matrix operations. So because every sample just have a lot of data in it. So like this is one sample, this is another sample, this is another sample, this is another sample, and then you have all these weight matrices, and then each weight matrix basically just do this vector multiplied by this matrix, and then you get this matrix as the product, and you can do it for all samples. So this is how in a regular neural network you basically get the next layer's output, and then of course you apply other functions to it. But the soul is, well, there is no most important, or one of the important parts is the matrix multiplication. And in this, when I was learning about that, there was a part where the kind of the example was a character recognition application, and what they just did is they got the image has like X and Y axis. Of course, it was a black and white, or rather a grayscale image, so there was no color, there were no layers. So they basically just flattened the image, every row in a huge row, like it was I think a 20 by 20 image, so you get basically a 400 elements wide matrix, and then you apply, of course, every weight have also like 400 elements in this column. So my thought was, why don't we just flatten the image into this very huge row? We can, if it's a color image, then you have like maybe 20 by 3, or if it's, I don't know, like a electron microscope image, and you have 10 different elements measured, and then you have all the 10 layers, and then it's gonna be, I don't know, maybe 1000 by 1000 pixels and just 20 element concentrations, so it's like 1000 by 1000 by 20, and you do like this, and then basically figure out like how to place each. So this, you have a huge vector here for each output pixel, which is mostly zeros, but then you fill in with the vector with the vectorized, so like the flattened form of this. So you get like this. For example, this one, it would be like -1, 0, 1, 2, -1, 1, 1, -1, and a lot of like, not like this, but there will be like zeros in the middle where, anyways. But this is not good because you have a lot of zeros. So what would happen actually is what I just wrote you here. So instead of flattening our images like this one into this very long vector and multiplying it with a vector where we are inserting the zeros, so these elements match up with the elements, like for example here, these elements match up with this. So if we want to do that, then we have this 1, 0, 1, 0, 0, 1, 1, 1. Yeah, point, point, point. And then, you know, this 1 is multiplied by this 2, and this 0 is multiplied by this 1, but then these two elements are not in this operation, and then you got the 0, you got the -1, and then these two elements are also not in that, so you got a lot of added zeros in there. That would be very wasteful of memory, of course. So what did they do? I was not far from the actual solution, because in the actual solution, not there, here, what they do is they flatten the kernel. They flatten the kernel, and for each new point in the final tensor, you get a slice of the image. So let's, for example, this part, you will have, okay, let's just copy. So for this element, to get this element, yeah, of course, we will ignore the bias right now, because the bias, as I said, you can consider like at the very end of this whole process. So here, let's take this kernel. We have the kernel that we are interested in. So because this is the first layer, this is the second layer, anyways. So the first layer will only have this part of the kernel, and we got this part of our image. What am I doing here? I am showing you all the processes that run on my computer. You can hack me now. So this is the part of the image. So when we flatten this out, of course, don't forget to flip the kernel. So this is how it will look like. -1, 1, 1, -1. So you can see like this is 2, 1, 0, -1, -1, 1, 1, -1. This is how this is flattened. So both of the layers, and this is our image. The image will be 1, 0, 0, 1, 1, 0, 0, 1. So this one goes here, this 0 goes here, and this 0 goes here, this 1 goes here, this 1 goes here, this 0. You get the point. Okay, so we got ourselves here this operation. I am doing right now. No, it goes there. Okay, and so let me fix all these really fast so I can do it for E with 5, F with 6, G with 7, H with 8, I with 9. So we fixed all this. Let me zoom in for you. So this is the first pixel here. So yeah, I will add the bias later, I told you. Let's just make these two biases 0. Okay, no, I believe that you can understand. So, and then, okay, so how do we get this part? So of course, there will be the other part. So this will be this. So this kernel is responsible for the second layer of our final matrix. So let me copy this. I should have just copied the format. So in this case, it will be also -2, 0, 3, -1, because we are going in the opposite direction. Don't forget that. 2, 1, 0, -1. So we are going this way. And this will be multiplied. Again, here you can check it's -3 because we have a -1 bias. And so we have both the kernels for both layers. So what else can we do? Well, what else can we do? We can also get the second pixel, which is coming from this part of our image. So this will be 0, 1, 1, 1, 0, minus 1, 1, minus 1. Damn. Why did I do that? That should have been here. 0, 1, 1, 1, 0, minus 1, 1, minus 1. And now you can see this is this point and this point. Again, this without, this will be 1 and 2. Bear in mind. And then we can go to the next pixel and do this again. And you can get it. And what happens is we run out of pixels. So we are going to do these two layers parallel because we put these two matrices here parallel. So that's okay. What if we go to the next sample? Then we are moving to the next sample. So let's just write dot 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 here. Then we will have our next sample inserted here. Dot dot dot. So what happens is that basically you get your two, these are the two separate kernels flattened. These are the two layers of the kernel, so this is the convolutional layers. This is, until this point, this is the two. Let me make it a thick. So until this point, this is one input layer, second input layer. Until this point, this is one row, and this is the other row of the matrix. And of course, it's going in this direction because we are the, but this one, so here we are going in that direction. I guess if I just cannot just write it like this, right? And this, okay, so the layers are going in this direction, and x and y coordinates are going backwards for the kernel. For the image, though, it's not like that. So this is, until this point, this is the first layer, so depth 1, depth 2 of the image. So we could make like a thick line here, and these are like parts. This is x1, or I mean x0, x1, and this is y0, y1, y0, y1. This is also, again, x0, x1, y0, y1, y0, y1. So this is how you flatten your matrix. And here you flatten from the other point. So how it looks, looks like this. And then when you get your final product, you will get a matrix. You'll have a problem, because here, the following problem you have is that this is like the first dimension, so the x dimension is the layer of the product. The layer is the first dimension, and the second dimension has x coordinate, y coordinate, or rather, if we are going from the outside to the inside, it's have the sample. So it's divided by sample, and then divided by x, and divided by the y coordinate. So here first sample, then it's going x, 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 and then y, 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 y. Simple enough. Not, I know it's not simple. But anyways, then you will have to make a tensor from there where sample is the first coordinate, layer is the second, and then xy. So you have to be very cautious when you are making the tensor, the four-dimensional tensor, from this two-dimensional vector, or two-dimensional matrix rather. So how did we implement this? So this is like the most simple implementation. It just reshapes the input in the 2D matrix for convolution based off the naive implementation with for loops. So we get a matrix, we get padding and strides. So when we pad, we just use the NumPy. Well, where did I go? Down the scroll bar. So we use the NumPy's pad function to make this padded x vector, which will coming from the matrix pad, and then it's got 0, 0. So because we are not padding in the first two dimensions, which are the sample and the layer, we are only padding for x and y dimensions, and we are padding same amount. So we get, this is like m is for the samples, d is depth, x, y. This is the shape, we get the shape of this matrix. Now the reshape is the kernel size will be squared. So the kernel size squared times the depth. So this is gonna be the x coordinate for the reshapes, and this should be the same as the y dimension for the flattened convolution kernel. So why is this? So this will be the y dimension of the flattened convolution kernels will be this long. So this will be, because we are working with all these square shaped kernels in this example, so it's the kernel size squared times the number of the layers. In this case it's gonna be 8. And this should be the same for, so this is the y coordinate for the reshaped kernel, and this is gonna be the same for our reshaped images. And this is going to be the image dimension of the reshaped image, so it's x minus the kernel size divided by stride plus 1. I am not sure if this is appropriate, so I think it should be x plus padding here. But anyways, so the reshaped image size, y will be squared the image. Yeah, because over the y, so the product image is also going to be squared. So this is going to, yeah, this should definitely be plus 2 times padded here. I'm kind of confused what I'm doing here, but yeah, this should be the, yeah, it's basically, it should be not the shape of the matrix, it should be the x pad shape, and in that case it's gonna work just fine, because now is the padding is included. So this is the original size plus 2 times the pad, and then this equation is true. So the reshaped image will be reshaped into this very long, instead of having a square, it will be very long, and the size will be this reshaped size squared. So the intermediate x is going to be this 3-dimensional matrix, have the same type as the original matrix had. So it's m is, don't forget, number of samples, reshaped x and reshaped y. And for each, so in this case, I did not flatten it like this. I just used a 3-dimensional tensor, and we're going through every I in the reshaped image dimensions and every j in the reshaped image dimensions sequentially. So this means that what we have done here, and we are calculating. No, where am I here? So no, this is what we were doing here. So we are going through the x and the y dimensions in the y vector in the y tensor, the final tensor. So for each position we will calculate this product that should be going there. So, well, no, it's not calculating product right now. It's just making the flattened image. So the x position is going to be I times stride. Yeah, so if we are striding more than one, then of course we are jumping by 2, jumping by 3. So x position is the I times stride. Y position is going to be j times stride. So don't forget these are the iterators in these 2 dimensions. This patch will be coming from the padded x. So it's this 2, both the depth and the sample is kept. So both in that dimension we take all the samples, all the depth at this position. So this is x position, from x position to the x position plus kernel size, from y position plus kernel size. So these are the positions. We got this from the iterators times stride, and then we get this patch will be what I just did here when I copied like this part. The only difference is that we copied this part together for this element, and this for like the xy is 0 is going to be these 4 elements, and for these 4 elements we need these 4 parts from these 2 samples and 2 layers, and then when we are going for this coordinate, then we will get for everything for these. So we will copy all these things. The patch will be like, for example, this patch got out from the tensor by this indexing here. And why this is faster, because this is a NumPy array, so this will be not handled by the Python interpreter, but this will be handled by NumPy, and NumPy is fast. And then we just reshape it. So we keep the number of samples and then flatten it out. So this patch will be flattened just like we flattened these patches here. So this patch, for example, this patch I'm having here is going to be flattened into this patch and this patch, but first they will be not like this. This will be in a horizontal shape, horizontally and over each other, like this kind of vector. Can I actually? I did not write that there, but if I just insert it, transposed. Yeah, so this is how it will look like, basically, in that after this reshaping. And we just get this reshaped part into this intermediate x, where we will have the first 2 dimensions to be the sample, the layer. No, it's a sample and the layer, and just basically this part. So this index I times reshaped image dimension plus the j this symbolizes like which position here in this part you are, based on the x and y coordinates. and then other 3 dimensions are just the layer and the sample, and then we transpose it, so we change the first 2 dimensions. So now from this being the sample and this being the layer, we change this with this reshaping, with this transpose. So first it will be the first dimension will be the layer, second will be the sample, and the third will be still this position, which is based on the x and y coordinates. So this is how it's gonna end up looking like this, or at least I think, because then we reshape it. So reshaped x, which is the reshaped x dimension is the same as the reshaped kernel, so y dimension. So this is going to be this dimension is reshaped like this, and the reshaped y times m. So basically puts all the samples next to each other, like one sample, second sample, third sample, etc. And I'm just kind of hoping that this is actually working, because now I have the feeling that it should be transposed one more times, but before reshaping it this way. But that's basically what this reshaping should be doing. And maybe it doesn't do that. I am not 100% sure, because I also implemented this other method from Stack Overflow, implement MATLAB's aim2 call sliding in Python. So what this one does is even more complicated than the previous one. So basically, I just try to get, so I make my padded X, I get the size of this padded X, and I just go to this image to column indexes with the size, the number of samples, the depth of the layers, size, and the stride. These are the important things here. And we are making an index matrix. So what we are going to do here is basically, instead of actually cutting out parts from our tensor and flattening them out, what we are doing is we are just telling Python that which elements are where. So basically we can address these tensors in a way. So we address it like first sample, layer, x and y coordinates. But it's in the memory of the computer. All these things are just stored as like one huge line. So basically we can address each point in this tensor just by one number. And so it's going to be y plus x times size plus layer times depth times size plus sample times depth times size times size, and this will actually be size times size. So why is this? Because this is how it's numbered 1, or at least it's coming from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So the y is always moving by 1. the x-coordinate is moving always by 4. So 1, 0, 4, 8, etc. And then we are going through layers, then it's always moving by 16. So it's size by size. 0, 16, 32. And that's going to be 48. Of course. And then when we are moving, well, it's actually just 2 layers. So it's 0 and 16. And it's going to be 0 and 32. So it's size by size by depth. So if I want to address this coordinate, this is, or let's say this one, which is sample 2, this number 1. In layer 1 is 0, and its y coordinate is 2, and x coordinate is 3. Well, actually it's 1 and 2 because, yeah, 0, 1, 0, 1, 2. So this is how it goes. So this is going to be layer 1, so it's 1 times depth times size, and depth is 2 times 4 plus 0 plus, so it's again 1, it's just 1 by 4, and then it's 2, and it's 2 by 1, so it's just 2 over 2. So this is going to be the 38th. So this is the 38th element of this tensor 1, 2, 3, 4. Well, 0, 1, 2, 3, 4, 8, 16. What? 8? What comes after 8? It's 12. It's 16. And then it's 32, 33, 34, 35, 36, 37, 38. So this is how we get this. So this is what we are doing here. We are trying to make a matrix for where we don't have these elements, but we have in each place we have which elements should be we reference from this tensor. And how are we going to do that? Indices, is it written like that in English? Okay. And how we are going to do that is by using NumPy's, not this one. I shouldn't be using Alt Tab, I just should be clicking on icons. So we are using NumPy's ranges. So what do we do here? And the comment says it. Indexes for the slices in one layer that is shaped like the kernel. So it's very simple. We want to get the slices out of the image which is shaped like the kernel, so like this. So how do we do that? We say it's kernel, and we get a range. There's a kernel size, so this is 0 and 2 in our example case. So we make a range that's basically 0 and 1 here. What do we do with this? We make a 2-dimensional vector out of it, which has just one size in one dimension. So we basically make a column vector from this, like this. This made a column vector. And then we get another range, which is also the kernel size. How does it do? So we have another range. This is going to be 0 and 1 again. So we got these two little vectors here. One is shaped like this, the other is shaped like this. What can we do? NumPy we say add them together. Oh no, this one is going to be, sorry, first we multiply a vector by a constant, like a scalar. So it's going to be size, which is the size of the input, the size of x, yes. So this is the size of x. So we have to multiply this by the size, which is 4. It's going to be 0 and 4. And then we add these together. And what NumPy does is NumPy feels like, okay, there is something fishy here. So these matrices, in general, linear algebraic sense, shouldn't be added together. But what NumPy does is distributes these two. So NumPy figures that, okay, this one has just one dimension, and then this one dimension size is 2. This one has 2 dimensions, and this is 2 by 1. It's 2 by 1 size. So we can match these sizes, and the transfers like 0, 1, 0, 1, like this. And then this one's going to be transferred like 0, 4, 0, 4, and then they add it together. This is how it will look like. 0, 1, and 4, 5. So what this is doing, it's very funny. So this is basically, let's see. Oh, this is the 0th element. This is the first element. This is 4th element, and this is 5th element in our tensor. Okay, let's see what happens next. So this is going to be an XA. So for XB, we'll make a range, which is a depth, which has the size of our depth. Okay, and then it also transposes it this way. So we have depth of 2, so it's not very, it's not going to be very difficult to imagine. But then, oh, it's multiplied by size squared, which is 16 in our case. It's going to be 0 and 16. We move it downwards one more. And then we add XA ravel. What does ravel do? Ravel just flattens it straight like this. So this matrix got flattened. It's very easy. And now we add this together. So here we add 0, so that's fine. That's 16, that's 17. That's going to be 20, and that's going to be 21. So what is this? These are the numbers of the elements here. So now we got these two numbers, these parts of the tensors by indices. Next one, gonna be another range transposed. And what is this? Find all possible slice starting points in one example. So what this one does, it goes from 0, it goes to size, so it's the size of the X matrix minus the KS, which is the kernel size, and adds 1, and goes by stride. So if we have a higher stride than 1, then it's going to be 0. For example, stride 2, 0, 2, 4, until we reach this number. So we have in our example stride of 1. So this is going to be, what is it going to be? It's going to be range 0 to size minus KS. So it's going to be 0, 1, I said 1, and 2 because size is 4. KS, so kernel size is 2 plus 1. So it's going to be 3. Okay. So this is going to be 3. And this is going to be multiplied by size again. So, okay, so that's 4, that's 8. What are we going to multiply this by? I'll just let me put it here. Is another range from 0 to so it's basically the same. It's going to be the same. Why is it the same? Because everything here is the same for x and y coordinates. We are working with squares. So we're working with squares. So if we have the same starting points Oh, but this one is not multiplied. Okay, so this is just 0, 1, and 2. I mean, I said 2. So when NumPy tries to add these together, then it's going to be 0, 1, 2. It's going to be 4. It's going to be 5. It's going to be 6. It's going to be 8. It's going to be 9. It's going to be 10. And what are these numbers? So these numbers are these elements of these tensors: 0, 1, 2, 4, 5, 6, 8, 9, 10. What do we know? So from each of these elements, we have a starting point for convolution. Like for example, this one gets with a starting point from here. This one gets from a starting point from here. This one gets from a starting point from here. So these are all the starting points where we can do the convolution. So these are the starting points, and these are where we can do the convolution. So these are the elements for one convolution. You can see it here. So these were the elements from the convolution, like these and these. And then if we could combine this with these, which are the starting points, so from this starting point we can get these elements. From this starting point we can get these elements, and so on. So we can combine these two starting points, find all possible slice starting points in all examples. Okay, that one was missing there. We are making another one. How many samples do we have? Of course, we have only 2 samples. In this case, it's going to be 0 and 1. And we, of course, multiply it by size by depth. Just like here, size by depth is going to be the sample number. So which is, in this case, 32, I guess, because 16 and 4 by 4 times 2, because we have 2 layers. And then, what do we have here? Ravel this. We're going to flatten this one out. Of course, so what we have here is, of course, can I just use the magic here? So this L is going to be fixed, and this H is going to be fixed. It's going to be too much for me to handle if I just want to write it in, but it seems like finding the mouse is also... Okay, so these are actually all the starting coordinates. So these are the starting coordinates for the first sample, and these are the starting coordinates for the second sample. So this one has all the starting coordinates, and this one has all the elements that are going to be convolved with the kernel. So the next step is, of course, ravel B and ravel D. So this one gonna be raveled and transposed, of course. Just like this, raveled and transposed. This one's going to be raveled and transposed too. And this is going to be this very nice matrix, which is, so this is the combination of all the possible starting points in the first example and the second example with all the elements. So this is first row, second row, first row in the second layer, second row in the second layer, and all the other starting points. So these are all the coordinates, basically, from this tensor that we return here as xe. And then what we do is we get the xe from this, and then get the np take, so NumPy take command, which gets the padded x tensor and gets all the elements that are described in this xe tensor. So the xe tensor looks like this. It has all the element references, and with the NumPy take command, the final matrix will have the same construction like this matrix, and then we will be ready to convolve this. And this is how this convolution works here. So let me just very briefly go back to my console here. Import convolve. Say k equals, well, do I reference this? Conv layer. And initialize. Wait. So output layer is 2, input layer is 2, kernel size is 2, padding, damn. I pushed the button, I pressed the key. Padding 0, stride is 1. Come on. I just imported convolve. What's the matter? Let me just run this file and then. Okay, now I have the convolution layer. So I'll just, let's say, k dot set kernel pw as weight and bias, k dot set in x. So we added the input, and then if I go to convolve, what does the convolve do? Where is my convolution here? So my convolution does get the x reshaped from the image to column, and then flattens the kernel by, so this one changes the direction of the kernel and then reshapes it to f. So it's going to be the what is f? The depth of this the filter number, convolutional filters number is the f. So that's going to be, anyway, that's the first coordinate for the convolutional kernel anyways, so that's why we don't need to switch around. Then we do get the flattened y from this neat matrix. So this at symbol in NumPy is used to symbolize the matrix multiplication. Then we add the bias, and then we just get what should be the size of this y, the y tensor, the y matrix x by y. What is the x and y size? And then we just reshape it. So you can see this is what I was talking about. The first one we get out is the filter number, then the sample number, and then y size. So we just switch back. We transpose the tensor by the first two parameters, and this is how we get the convolution operation done here. So basically we do this matrix operation, we add the bias, and then get these flat y's, the flattened y's, into our matrix again. But because of this, we have to change the axis numbers, the axis ordering. That's the transpose. That's what the transpose do. And let's see, y2 equals k dot convolve. So let's see, y2 minus y. And this is a lot of zeros, which means we got the same operation. Everything is the same as we did with the naive implementation. So we can be proud of ourselves. And I could just change this to the naive, so the image to column loops, and we could check if that one works as well, but I am not convinced that this is implemented correctly here. So it's not something I'm gonna show you right now. So this is going to be the end of this video. So I hope I could shed some light on some things concerning the convolution operation and how it's implemented, because I think this is kind of fun, this indexing, how it is very fast to make this index matrix in NumPy instead of just looping through in Python. So because NumPy is of course very fast, and Python, the Python interpreter is not that fast. So these kind of things we have to consider when we are writing our code in Python. And next time I will be doing the backpropagation in this convolution. And there will be something that was very hard for me to find on the internet. So I hope in the next video I can shed some more light on some more things. And I'll see you then. Bye bye.